Hello friends, in this video we will perform one of the DC experiments, that is binary phase shift keying. Now basically we will first see what is phase shift keying. As we have seen in analog communication that in phase modulation the phase of the carrier changes in accordance with the instantaneous amplitude of the modulating signal. Same principle is applied here in phase shift keying. The thing is, when the bit pattern changes from 1 to 0 or 0 to 1, the phase shift of the carrier signal changes. Now, in binary phase shift keying, when suppose for logic 1 the phase shift is 0 degree, then when the bit changes from logic 0 to logic 1, the phase shift changes by 180 degree. I can show you one of the sample input signal for Bpsk. As you can see, I have shown the input pattern here, that is 10110000, and I have shown a carrier signal here. Now as you can see, for bit 1 the signal is as it is, that is it is having 0 degree phase shift. Now when the bit is 0, it is having 180 phase shift, that is it is inverted. Again for bit 1 the phase shift is 0 degree, and again for the remaining 0 bits it is 180 degree. So you can say that for logic 0 the output will be inverted of the original carrier signal. Now we will observe the behavior of Bpsk signal on hardware. Now let's connect the connections. First we will observe the input signal on DSO. So here is the pattern generator. We are having two patterns, so we'll first observe first pattern. As you can see, it is showing the same bit pattern which I have showed in the previous example, 10110010. Now let's check the carrier signal. We can observe the carrier signal at the multiplier PSK generator. So we'll connect this pin here. You can observe the carrier signal here. It is a pure sine wave. Now let's observe the Bpsk signal on the kit. Now we'll give the input pattern generator to the first input of OR gate. Now we have used here OR gate. This is because when we switch on the kit, the receiver knows that the first bit is going to be 1. So to avoid inverting of data at the output of the receiver, that is when we get the received data at the output of the receiver, we shouldn't get inverted of the original pattern. So to avoid that, we are using here OR gate. Now we'll connect the output of OR gate to the input of the multiplier PSK generator, so that we'll observe the Bpsk signal on its output. Now let's observe the Bpsk signal. Now as you can see, as the bit changes from 0 to 1, there is a phase shift. When the bit was 0, the phase shift was 180 degree. Now when the bit is 1, the phase shift is 0 degree. You can also observe for when the bit changes from 1 to 0. So we'll shift this waveform. Now as you can see, when the bit changes from 1 to 0, the phase shift is changing from 0 to 180. Now let's observe the spectrums of the input pattern and the Bpsk signal. So let's connect the first channel of the DSO to the input signal generator. And now let's observe the spectrum on DSO. So let's observe the spectrum of the input pattern. Now we'll press the map button. So here we will now change the window to Hanning and shift the spectrum towards the right. Now expand it. Then press the stop button and zoom it to into 10. So we'll observe the first null to get the bandwidth of the input pattern. Now press on the cursor button, change the source to math and change the type to frequency. Now adjust the first cursor to 0 Hz. You can see here the first cursor is adjusted to 0 Hz. Now let's adjust the second cursor to the first null. So this is the first null here. We are getting the first null at 1 kHz. That means the bandwidth of the input pattern is 1 kHz. Also, you can calculate the bit period from it, that is 1 upon 1 kHz. That will come out as 1 millisecond. We can also observe the bit period in the time domain signal. To observe the Bpsk spectrum, connect the first channel of the DSO to the Bpsk output, which is generated after multiplier Psk generator. So you can observe the Bpsk signal here. So the Bpsk signal is connected to channel 1 of DSO. To observe the spectrum, we'll press the map button. Now we'll adjust the spectrum. So we'll press the cursor button to measure the frequency. The source should be mapped and the type should be frequency. So first we'll observe the center frequency, that is the carrier frequency. The carrier frequency is observed at the maximum gain lobe, that is the peak lobe. So as you can see, I've adjusted the cursor to the peak lobe and it is showing 20 kHz, that is the carrier is of frequency 20 kHz. Now let's adjust the cursor to the first null at the left side of the center lobe. As you can see, I'll pause it so that you can observe it clearly. As you can see, the first null is observed here at 19 kHz. That means the first frequency observed here of the first null at the left side of the center lobe is 19 kHz. Now let's start again. I'll select the second cursor and I'll adjust it to the second null. Now I'll pause it. As you can observe, the first null after the center lobe is observed at 21 kHz. That is the first null is the second frequency of the first null after center lobe is observed at 21 kHz. Now, as we have studied in theory that the bandwidth of the Bpsk signal is twice Fb. So we observed earlier that the Fb, that is the frequency of the input digital pattern, was 1 kHz. So by using the formula 2FB, that is 2 into 1 kilohertz, we will get 2 kilohertz frequency bandwidth. To observe the bandwidth here, we will subtract this frequency from this frequency to get the bandwidth. So 21 minus 19, that is 2 kilohertz bandwidth. So we can verify by both the methods, that is by using the formula 2FB and also by observing the spectrum and by subtracting these two frequencies. Now we have to demodulate the Bpsk signal. So we know that Bpsk uses synchronous detection, that is, the carrier is recovered at the receiver side. So now we'll connect the Bpsk output to the input of the receiver. Now I'll show you the block diagram of the receiver. Here we have a squaring circuit which will square the input signal to the power of 2. This is a bandpass filter which is centered around the frequency 2fc, that is the twice of carrier frequency, and we have a divide by 2 network to divide the frequency by 2. Now we'll observe the squared signal here. Now we'll connect the channel 1 of DSO to the output of squaring circuit. So we can observe the squared signal here. It is irregular in shape, so we can determine the frequency of it. So we'll now observe the output of the bandpass filter. So this is the general block diagram of the Bpsk receiver. So as we know, the equation of Bpsk signal is root 2 times b of t cos of 2 pi fct. Now after squaring the signal, we will get the equation as root 2 b of t of whole square cos square of 2 pi fct. Now we know the trigonometric identity that cos square theta is equal to 1 plus cos 2 theta by 2. That is, we'll split the denominator term as 1 by 2 plus 1 by 2 cos 2 theta. So we can write cos square 2 pi fct as 1 by 2 plus 1 by 2 cos of 2 pi fct. Now we have a bandpass filter here whose center frequency is 2fc. Now we have here the signal 1 by 2 cos of 2 pi fct. The bandpass filter will pass this signal and reject this signal because this is a DC signal and we don't require a DC signal. So this is the general block diagram of Bpsk receiver. We have a squaring circuit, a bandpass filter and a frequency divider by 2 network. Here we get the original carrier which is used to modulate the digital signal at the transmitter side. Here we have a synchronous multiplier which is also called as synchronous demodulator. It has two inputs. One is the Bpsk signal and second is the recovered carrier obtained from this unit. The synchronous multiplier multiplies the carrier signal with the Bpsk signal to obtain the digital signal here. Now this digital signal is not the original signal. To obtain it, we use a phase comparator, that is the integrate and dump comparator, to obtain the original data signal which is used at the input. The bit synchronizer is used to take the samples of the comparator. Now let's observe the bandpass filter output. We'll connect the DSO channel to the output of it and we'll connect the output of the squaring circuit to the input of bandpass filter. Now let's observe the output of bandpass filter. So this is the output of bandpass filter. As you can see, the output is not in shape. So we have a knob on the kit which will adjust the bandpass filter output to in its shape and in maximum value. So I'll adjust the knob of the bandpass filter. So I'll adjust the knob of the bandpass filter to get maximum output at the DSO. So we have adjusted the knob so that we get maximum amplitude at the output of the bandpass filter. Now we observed that the carrier frequency was 20 kHz. Now we also saw in the equation that after squaring we use the trigonometric identity and obtain the equation as 1 by 2 plus 1 by 2 cos of 2 into 2 pi fct. That is, we should get twice the frequency of carrier. Now let's check whether we are getting 40 kHz. We'll press the measure button here and we'll observe the frequency here. So we are getting 40 kHz as the output frequency of bandpass filter. So now we'll connect the output of bandpass filter to the frequency divided by 2 network. We'll connect the channel of DSO to the output of the divided by 2 network, and we'll connect the output of bandpass filter to the input of divided by 2 network, and we'll observe the output of divided by 2 network. So this is the output of the frequency divided by 2 network. We'll adjust it on the screen so that we can get a proper view of it. So this is the output of frequency divided by 2 network. Now, as the name says, divide by 2, so it will divide the frequency of the output of bandpass filter. We have got 40 kHz as the output frequency of bandpass filter. So dividing it by 2, we should get 20 kHz. As you can observe here, we are getting 20 kHz as the frequency. Now we'll observe the demodulation process of Bpsk signal. Now we'll connect the DSO channel to the output of the receiver. Now, as we know that the receiver of Bpsk has two inputs, that is the synchronous multiplier has two inputs. One is the recovered carrier and the second is the Bpsk signal. So we'll connect the recovered carrier to the input 1 of phase comparator and the Bpsk signal, which is observed here, at input 2 of the phase comparator, and now we'll observe the demodulated signal at the output. So we can observe the demodulated signal here. Now earlier I had given a bit pattern while I had drawn on the waveform, that was 1 0 1 1 0 0 0 0. You can observe these bits here. So we can verify that this is the original modulating signal which was used at the transmitter side. It may happen that this signal may get inverted, that is the output of this receiver may get inverted. So you should do one thing: turn off the kit, wait for 10 to 15 seconds and then turn it on so that we can get the original signal. As I had mentioned of the OR gate, that when we switch on the kit, the receiver knows that the first incoming bit will be bit 1. So it verifies that the output is original modulating signal used at the transmitter side. So this is all about the Bpsk experiment of DC. Thank you very much for watching.